Lecture 7B, control volume form of the conservation law. Uh, Example, we will do starting with example 6.6. A mass rate of flow into a steam turbine is 1.5 kg per second, and a heat transfer from the turbine is 8.5 kg. The following data are known for the steam entering and leaving the turbine. So the inlet condition is pressure is 2 megapascal, temperature is 350 degrees centigrade, the velocity is 50 meter per second, and the elevation from the reference plane is 6 meter. The exit condition is 0.1 megapascal. The quality is 100%, which means like we are in saturated vapor. The velocity is increased to 100 meter per second, and the elevation plane is actually 3 meter. So we have got a turbine which is actually open system in which there is a mass entering into the system and there is a mass leaving into the out of the system. There will be some energy entering into the system and there will be some energy leaving the system. So this is a simple example of a steady flow energy equation. The mass flow rate is given, which is 1.5 kg per second. Say like the heat is transfer from the turbine. From the turbine would mean like there would be negative heat transfer out of the system, which mean like heat is actually going out of the system rather than getting into the system. So looking at the steady flow energy equation, we have got Q minus W would be equal to ME minus, and that's minus MI, and so on and so forth. So just rearrange that equation in terms of this one. So that means like Q is here. Q is given, which is over here 8.5 kilowatt rate of heat transfer. That means like kilojoule per second it is. There is a worked we need to find the power. So power mean like rate of doing work we need to find out. That is somewhere here. There is actually velocity inlet, it is given. Z at inlet is given. Velocity exit is given. Z at inlet, Z at exit is given. The only unknown, apart from the work done, we have got the enthalpy at the inlet and enthalpy at the exit. We have already got the mass as well, which is 1.5. As for the steady flow, the mass rate is constant throughout, which is 1.5 kg per second. So finding the kinetic energy, finding the potential energy would be easy, just putting the value and getting the answer itself. Uh, Now finding the enthalpy at the inlet. So at the inlet, we have got a steam of which the condition is given. So the condition is 2 megapascal and 350 degrees centigrade. So obviously we will be moving to steam table, and looking at steam table we have to find the 2 megapascal. So just looking at the pressure table, for the 2 megapascal, if you can check the saturation temperature is 212.38, while our given temperature over here is 350 degrees centigrade. So that means like our 2 megapascal 350 degrees centigrade, it is in a superheated region. So going back to the superheated condition for a 2 megapascal, and that 2 megapascal is over here, 2 megapascal and 350 degrees centigrade, which is somewhere at the fourth column, 350 degrees centigrade. We have got the condition, which we have got the velocity, we have got the volume, we have got the enthalpy, and we have got the entropy. So for the initial condition enthalpy at 2 megapascal 350 degrees centigrade, the enthalpy is 3137.6. so going back to over here, 3137.6, so might be it is using different steam table and we have got a little bit different one. So we have got the inlet enthalpy anyway. So that's enthalpy is now from the steam table. For the exit enthalpy, if we can say, at the exit condition, we have got 0.1 megapascal, and the condition is given with the quality is X. X is equal to 1, which means like we have got the saturated vapor state. Saturated vapor, so going back to the saturated steam table, and the saturated steam table we have got to 0.1 megapascal somewhere here. Oh, sorry for that. It is superheated condition. So 0.1 megapascal in a saturated pressure table somewhere here. We have to look at the enthalpy, and that enthalpy is Hg or Hv, it is called at over here. So that enthalpy is over here, so somewhere here. So that is 2674.9. Now going back to the question, 2674.9 something, and somewhere in the book it would be somewhere here. So we have got the inlet condition, we have got the exit condition, we have got the inlet kinetic energy, potential energy, exit kinetic and potential energy. So you can just put the value, get the answer, and you would be finding like the work done would be equal to 678.2 kilowatt. Use the per kilogram, and yes, obviously it is actually so. Is using different formula, you can actually use anyway. So going back to the going to the next question. Now we have got the air which is going into the control volume. Now air have got the velocity of 20 meter per second, temperature of 260 Kelvin, and a pressure of 75 kilopascal, with the mass flow rate of 500 kg per second. Flow into the jet engine, so flowing into the jet engine, and it flow out as 500 meter per second velocity, 800 Kelvin temperature, and 75 kilopascal pressure. So the pressure remain constant. What is the change in a power inflow of kinetic energy? This is just a very simple question. You have to look at what is actually required. So the required is actually change in the kinetic energy. So the change in kinetic energy is equal to half m c2 square minus c1 square. So we have got the inlet velocity, we have got the exit velocity, just putting the value, getting the answer, and you have got the answer. Change in kinetic energy would be equal to 624 kilowatt if you are multiplying with the mass, so that would be kilowatt. If you are not multiplying with the mass, that would be kilowatt per kg. So just a very simple, I would say, discussion on this one. Why there are so many other information over here, like this one, like this one. So make sure these are just like, you do not, if you do not need it, just do not actually use it. The only thing is actually you have to concentrate on what is actually required. Moving to the next question, question 6.45. A small expander, we have got the expander or turbine with a heat transfer. So there is actually heat transfer in and out of the turbine somewhere. Has a 0.5 kg per second mass flow rate of helium entering at 1000 kPa of the pressure, 550 Kelvin of the temperature, and it leaves at 250 kilopascal of the pressure and 300 Kelvin of the temperature. The power output of the shaft is 55 kilowatts. Find the rate of heat transfer, neglecting the kinetic energy. So there is no need of kinetic energy, and also there is no mention of the potential energy changes as well. So we are ignoring the potential energy changes as well. So that means like our equation, which was Q dot minus W dot, is equal to M, and that was enthalpy, kinetic energy, potential energy. We are just left with the enthalpy changes only. So that's the equation now. So that means like for a steady flow, we have got this one. Just solving it for Q. So that means like just leaving, just taking this work done on this side. So we'll be having the equation somewhere here. For a helium, which is actually assuming to be an ideal gas, if you remember, change in enthalpy was equal to Cp delta T. So that means like we need to find the Cp of helium, or we need to find just find it from the table anyway. So for the helium, Cp is equal to 5.193 kilojoule per kg Kelvin. Change in temperature is inlet and exit temperature is already given, so you can actually have put the value in this equation and getting the answer, which is minus 0.9, sorry, no, minus 9.9 kilowatt. Minus would be mean like there is energy, there is a heat transfer taking out of the system. So question 6.79, a steam turbine receives water at 15 megapascal 600 degrees centigrade at a rate of 100 kg per second as shown in this figure. In a middle section, 20 kg per second is withdrawn at 2 megapascal and 350 degrees centigrade, and the rest of the steam is exited at 75 kilopascal with a 95% quality over here. Assuming there is no heat transfer and no change in kinetic energy, find the total turbine power output. So this is definitely not the mass is actually entering into the system, but it is leaving the system from two different points, which is actually at state 2 and state 3. So if I'm looking at the continuity equation, that would be m1 dot rate of mass change is equal to m2 over here and m3 over here. So it's a like 100 kg mass is entering to the system, kg per second mass is entering into the system, 20 kg mass, kg per second mass is leaving at state 2, and the rest, which is actually 80 kg per second mass, is leaving the system at state 3. So let's find the first of all, let's find the equation for it. So again, looking at the equation, Q minus W dot would be change in Q minus change in W, that would be equal to M dot into H2 H exit minus H inlet. That is when we are talking about a simple inlet and exit, when we have got one inlet and when we have got one exit. There is no heat transfer. Yes, so there is no heat transfer, that would be 0. So that means like kinetic and potential energy already is actually taken at 0. So that means like W would be equal to M dot and H1 H inlet minus H exit. So that means like just rearranging itself. Now the thing is like at the inlet, if I'm saying, let's assume at the inlet we have got this equation would not be same as for this current problem. So we have got mass at the inlet, which is 1, mass at 1, enthalpy at 1, minus we have got enthalpy mass at the exit and enthalpy at the exit, but we have got two different enthalpies and masses. So that is mean like inlet would be here m1 dot h1 minus m2 h2, and there is another mass leaving the system, which is sorry m3 and h3. That means like we have got the inlet enthalpy minus the exit enthalpy. But in our exit enthalpy and mass with the mass, we have got M2 and we have got M3. So now that equation would be equal to W dot would be equal to this equation now. Now this equation become now a little bit simpler now. M1 is given, which is actually equal to 100 kg per second. H1, which is 15 megapascal and 600 degrees centigrade. So 15 megapascal, 600 degrees centigrade, just looking at the steam table, you will find out that 15 megapascal, 600 degrees centigrade is in a superheated condition. Go for a superheated steam table at 15 megapascal, 600, find the enthalpy and you will find this enthalpy. For the same 2 megapascal 350 degrees centigrade, as we have done in a previous example, at 2 megapascal the saturation temperature is around 202 something, so 350 would be in a superheated condition. So H2 is again in a superheated condition, just find the superheated enthalpy at state 2 as well. At state 3 we have been given pressure and we have been given quality as well. So at 75 kilopascal or 0.075 megapascal, find enthalpy HF and Hg, and putting this equation, which is H3 would be equal to HF plus X HFG. X over here is 95% quality. Just putting the value and you will find the enthalpy, which is over here. Now once you find the enthalpy, put all these things, all these value in this equation or the equation you have just derived now, and the work done would be equal to 91.65 megawatt. Hope you will find this a little bit easy. If there is any question, do let me know in your classroom and I will be able to find the answer. Thank you very much.